Hello everyone, I'm on YouTube again. So I made this recitation into another video because I'll be out of town on Tuesday, and I still hope I can help you with preparing the exam 2. And the material we're going to use today is one of the previous exam 2 covering the entire heat and mass convection part. So I uploaded 2 copies of this past exam, one without the solution and one with the solution. So depends on your time budget. So if you have time, I hope you can try to do it once without looking at the solution and see how familiar you are with the contents. But if you are tight with the time, of course, you can directly go to the solution, see what type of problem we may have. And I think, although actually I haven't seen the actual second exam problems yet, so I cannot make any. I wasn't able to make any comment. But they will basically cover very similar content because the key points are those points we cover in the lectures. Right? So the problem 1 is compiling a lot of different topics, small concept problem. The first one is about velocity and thermal boundary layer. Says the Prandtl number is 7. And what do we know about the Prandtl number? By definition is the kinematic viscosity over the thermal diffusivity. The kinematic viscosity, we can also see that as the momentum diffusivity, right? This one equals to 7 is saying the momentum, the velocity basically, more likely to diffuse into the free stream than the alpha, right? Than the heat, right? So in laminar part is dominant by this Prandtl number, so we know the thermal boundary layer must be thinner than the velocity boundary layer. But after it transits into the turbulence at xc, so this is turbulent, this is laminar. After it transits to turbulence, because the fluid flow itself have a very strong mixing effect. So the Prandtl number is not dominating anymore. So the mixing makes thermal boundary layer and velocity boundary layer merge together. This is part A. Part B is asking about the hydrodynamic entry length and thermal entry length. Basically, it's also comparing the velocity distribution and thermal distribution. Now this case is internal flow. So we know when it enters the pipe there's an entry length, and when the two boundary layer merges, and after a small distance we can say, okay, it's fully developed flow, right? So similarly, the velocity and thermal boundary layer will develop also depending on the Prandtl number. Depends on your Prandtl number is close to 1 or close to 0 or very large. All these cases are possible, right? All these cases are possible. And part 2 is asking the Nusselt number, laminar fluid flow inside a circular tube. What was the average Nusselt number comparing with the local Nusselt number? So we know when it's entering, the boundary layer the effective boundary layer thickness is thinner, right? It's this one. And when it reaches a fully developed flow, after this, the boundary layer on both edges merge together, it's actually thicker. So we know the entry region, the convection coefficient should always be larger. And when it goes to, when these two merges, it will be a constant. This is the distance into the pipe. So if we look at here, we should know that the average of this heat transfer coefficient should always be smaller than this value. The entry region have a higher H. Next one is assuming another planet. Everything is the same, only gravity is different, and it's asking what is the free convection heat transfer coefficient. how does this one change? And basically we know this free convection is driven by gravity. The stronger the gravity is, the stronger the free convection is. So the problem says the other planet has a gravity smaller than the Earth, means in the same scenario, free convection is weaker. And of course we can write down the equation, and we can first look at the Rayleigh number. So everything else is the same, only this one differs. So the Rayleigh number of that planet is smaller, and Nusselt's number will also be smaller. If you want to. Part D is about the boiling curve. First free convection, and then two zones. This is the critical heat flux. It's like this. So the first blank is asking, what if the chip generates 70 watts? And we can calculate the heat flux is 7. We look at the curve, we find, okay, it must be this point. And then the corresponding temperature, we can read that the excess temperature is 10. And we know the saturation temperature. The saturation temperature is how much is 80. And we'll know the actual surface temperature is 90. Okay. The second one says the surface of the chip doesn't want to exceed 150 degrees C. So corresponding with delta T max will be 150 minus 80, which is 70. When we find the point 70, find out okay, it's here. And then we look at this curve. It's asking us what is the maximum power the chip can dissipate. And we found okay, it's the critical heat flux. It's corresponding to 10 to the 6 watt per meter square. And we will know the maximum heat allowed will be 100 watts. So I have a question. So what if your chip dissipates more than 100 watt of power? I'll give you 5 seconds. It will be here, right? This is say if we are controlling the surface power, the boiling will not undergo this part and will directly go to the boiling crisis and reach the fume boiling part. Be somewhere here. And this will correspond to a very high temperature. So if you really have, so for those cases, one thing is to make a smarter electrical design to reduce the power power consumption. The other one is to basically extend the surface, so we are not limited by that area. Maybe by putting some fins, or simply extend the surface. Let's say this is the chip. Okay, this is the chip, and just put a large metal plate on the top, right? And this one is immersed in the fluid. This immersed in the fluid. Some boiling is happening. Okay, that's all for problem 1. Most of them are concept problems. Okay, now let's look at problem 2. Obviously, it's a flat plate external convection problem. So the free stream temperature and velocity are given, the surface temperature is given, and the length of the plate is given. And the other thing is the dimension into the board, which is not very important, right? Which is finally time that when we want to evaluate the Q. So when we get this information, the first thing we can check is obviously the Reynolds number to see whether it's a laminar or turbulent or with the transition in mixed case. And that's exactly what part A is asking for. So we can directly go to calculate the Reynolds number. It's a flat plate, so the characteristic length is just the length of this plate. And I think we found it. This one is laminar. Found okay, it's laminar. Part 2 is asking which location of the plate have the highest surface heat flux. So this one is still a concept problem. We know the boundary layer here is the thinnest, so so at the leading edge it must have the highest surface heat flux. And just I want to remind you the entire picture. So this is the distance from the leading edge. We have one thing called local convection coefficient H, right? This one will look like this. What is here? Dashed lines. What happens here? This is the turbulent transition zone, right? So when it turns into turbulence, the heat transfer, also mass transfer enhance. But after it turns to turbulent, it's still developing, and the heat transfer coefficient further decays. This is the local heat transfer coefficient. We also have another thing called the average heat transfer coefficient. We can also plot with different length of the plate, or the different length you interest. So that is directly average of this curve. So here is high, so I'll use another cutoff pen. So it will be always higher than this number. And then what happens here at the transition zone? So when we do the average, we take integral, right? Although here is not continuous, but when we take the integral, it continues. Just it's not smooth anymore, right? And then this part actually goes this way. This is the average heat transfer coefficient. This can also be a function of x. And the part B is asking which part have the highest, and that is this part. You will never exceed this number because your boundary layer is infinite. Part C, calculate the average Nusselt number. We know it's laminar, we know the Reynolds number. Prandtl number is also in the given table. The property is evaluated by this film temperature, which is average of the far field free stream temperature and the surface temperature. And we just find the correlation for this one. And be careful, this is the average part, right? And part D, there is some electrical heating within the plate, and this heat is taken away by the convection. So we will know the electrical heating power by energy balance should equal to the heat of convection. And this one can be easily calculated by Newton's Coulomb law. And this one is taken from the Nusselt number. Right. That's the procedure. And the second part of this problem is the evaporation, which is a mass transfer problem. And by the heat and mass analogy, we will know that for heat transfer, we know this correlation. So for heat transfer, we have this one. And directly we can get, for mass transfer, we have the mass version of Nusselt's number, which we call the Sherwin number. And it's in the same form. So here, the coefficient and index will be the same. That's because of the analog. And similarly, we can calculate this number equals to something. And then by definition, we can get the mass transfer coefficient equals to something. And in this case, it's actually simpler. We don't need to deal with the relative humidity thing. So here, the relative humidity equals to 0, which there's no water. And here we have a water fume. So right next to the surface, we assume is say in equilibrium, right? So the property here is just the equilibrium property. The density of water vapor will be just the water vapor density at the equilibrium at this temperature at atmosphere pressure. And now we can calculate the mass transfer rate of water, which is a very similar form of the Newton's cooling law. This is the rho at the surface, which is also the saturation, and this one is 0 because it's dry air. And then we know evaporation takes away thermal energy, and the energy taken away by the evaporation will be the mass flow rate. I'll just write it back. Times the latent heat, right? From fluid to gas phase. And remember, the heat transfer is still existing when we have the water there. So now this power, this electrical heating power, will be the convection we calculate at part 1, plus the heat taken away by evaporation we just calculate here. Okay, now let's look at problem 3. It's a heat exchanger problem, and so here overall heat transfer coefficient is given, and the shape is given, so we can calculate the total area. And here we know the mass flow rate and the specific heat for both flows, and we know the interest temperature. So the interest temperatures. So this we call this kind of problem a performance problem, right? So that is saying we know how we already designed the heat exchanger, and we want to know how much it performs. In this case, it says this concentric tube, all these things, but we just know it's a counterflow heat exchanger. And actually, there are 2 ways to solve this. It's a counterflow, so it's a 1D case. So we can use the log mean temperature difference method. Log mean temperature difference method, we have 3 equations, right? One is saying the heat transfer rate will equal to this UA, which works as the HA of the traditional convection problem. And the temperature difference here is not the difference of any combination of these 2, but instead we call a log mean temperature difference. And this one depends on whether it's a counterflow or parallel flow. It's a function of these 4 temperatures. This is the first equation. Second and third one is saying the heat transfer rate, the transfer in this heat exchanger will equal to, one is the heat capacity rate times the temperature difference of the hot side. This is how much heat is lost from the hot side, right? This one also equal to how much heat is gained on the cold side, which here is T cold out, T cold at the outlet, and minus the temperature on the cold side inlet. So 3 equations. We don't know the total heat transfer rate. We don't know the 2 outlet temperatures, and 3 equation solves 3 unknowns. Oh, by the way, this one also inside the log mean temperature difference, we also have these 2 unknowns. 3 equations solve 3 unknowns. And when you solve all these 3, our problem, our part A is asking this one. Part B is the broad stream, which is the cold side, which is this is the part B, right? After you solve this one, you can get the solution for part A and B. And third one is plotting this case. So generally, this is the temperature. The hot side temperature will decrease. The cold side, this is the hot side. Cold side temperature will increase as the flow direction. These 2 are given. These 2 can be calculated. We also have the second method, which is the effectiveness NTU method, which is more generalized. It can deal with tube shell heat exchanger, cross-flow heat exchangers. And that is the method our solution gave. So what can we do there? Again, this is a performance problem. So we start with the design, and we can first get NTU. And by definition, this is the UA. Just in case you can. Concentric tube, the actual transfer, the actual transfer surface area will be pi d. D is the tube inside. The diameter of the tube inside times the length of this heat exchanger, divided by heat capacity rate on the side that the absolute number is smaller. First get NTU because we know the design. And then we go to the table in the textbook. We find the effectiveness is a function of the NTU, also the ratio, right? Also the ratio of the heat capacity rate. And this function we have to find the case for the counter flow. Now we have this epsilon. And epsilon, by definition, is the actual heat transfer rate divided by the maximum possible heat transfer rate, which is, in this case, after simple calculation, we know that the cold fluid, which is the blood have a smaller heat capacity rate, which if you have a perfect heat exchanger, the temperature on the cold side will exit as the hot side entrance temperature. And this much heat is what this Qmax is. So this one should equal to capacity rate at the smaller side. This one is hot. This hot side entrance is the hottest, right? And the cold side entrance is the coldest. Equal to this one. We know this number, and then we can get this Q, which is part A. So we use this one, we can get the outlet temperature on the cold side. And then part C is the same. We have two ways to solve the same problem. I want to give a last comment that maybe you have already seen in problem 2 and 3 with the problems with more calculation. Actually, the procedure, you can extract a standard procedure to solve this type of problem no matter what numbers are given to you. So I hope you can get very comfortable solving this kind of problem with standard procedure. This will save you a lot of time.